Last time we looked at equilibrium. Equilibrium is this state where in a reversible reaction, the rate of the forward reaction is equal to the rate of the reverse reaction, and the concentration of the products and reactants are constant but not necessarily equal. So when we're talking about equilibrium and changing the equilibrium or making changes to an equilibrium reaction, we use terminology which is a little different. So we talk about left and right, and when we talk about it lying to the left, that means that if it lies to the left, there are more reactants than products, and if it lies to the right, there are more products than reactants. And if we want to shift it to the left, that means it makes more reactants, and if we want to shift it to the right, that means it's going to make more products. So it's right and left as you're looking at your screen, the left being the reactants and the right being the products. The position of equilibrium can be calculated, but that's advanced higher. We're not going to deal with that just now. We're just going to look at how shifting the equilibrium happens based on Le Chatelier principle. So here he is, Henry. He said, when a system at equilibrium is subjected to change in concentration, temperature, volume or pressure, the system readjusts itself partially to counteract the effect of the applied change, and a new equilibrium is established. Basically, what he said is, whatever you do to the reaction, equilibrium will shift to undo what you've just done. So if you make a change to the system will try and fix the change that you've just made to get back to its balanced state. Equilibrium can only be established in a closed system. So what actually is a closed system? So let's imagine a reaction between sodium carbonate and hydrochloric acid. If we do it in a beaker, sodium carbonate is going to react with hydrochloric acid in a neutralization reaction. It's going to produce a salt, water and carbon dioxide. If we do this in a beaker, an open beaker, the carbon dioxide gas is going to escape. So everything in that system is not closed. There is a possibility of escaping. That can, this reaction in a beaker cannot be a closed system, therefore equilibrium cannot occur. So this is called an open system. But if we did the same reaction in a conical flask with a bung, then the system's now closed, the carbon dioxide cannot escape, therefore the equilibrium is established within that conical flask. Changes in concentration, pressure and temperature can all alter the position of an equilibrium of a closed system, remember. A catalyst will increase the rate of attainment of the equilibrium, but it does not actually affect the position of the equilibrium. So a catalyst is only going to speed up the reactants achieving equilibrium. The effect of changing conditions can be explained using changes in rates of forward and reverse reactions and the position of equilibrium. When we're answering questions on this, we want to see what the changes are going to do to the position of equilibrium and also what the changes are going to do to the rate of the forward and reverse reactions. The SQ like you to use both to gain those marks. So first we're going to look at the effect of temperature. Now normally we would do this in experiments in class. I'm going to try and talk you through the experiments, but I do have in these slides links to Scholar where you can do an animation of what happens on a molecular level within the experiments, and then at the end of the lesson I've got some links to another YouTube video where they have done the experiments. Unfortunately I can't do these experiments in my own kitchen. So first thing we want to do is be able to describe how temperature affects the position of the equilibrium. So we've got nitrogen dioxide in a equilibrium with dinitrogen tetraoxide. Now the NO2 is brown, whereas the N2O4 is colourless in their natural states. At equilibrium they kind of go this kind of medium brown colour. And we use this spectrum of brown to work out where the equilibrium is sitting at any given time. So it's kind of somewhere in the middle of the colourless and brown. So to explain how equilibrium shifts with temperature, the enthalpy change must be known. This makes sense. We know that every reaction has an enthalpy change. It is either exothermic or endothermic. If it's exothermic, it's going to release heat to the surroundings. If it's endothermic, it's going to take in heat from the surroundings, cooling it down. So every equilibrium reaction has one direction exothermic, the opposite direction endothermic. When you reverse an exothermic reaction, you get an endothermic reaction, and vice versa. So if the forward reaction is endothermic, the reverse reaction will be exothermic. In this case here, our forward reaction is exothermic and a reverse reaction is endothermic. So we're going to add this file to cold water and to hot water and see what happens. In the when we add it to cold water, the gas is going to become a lighter brown. When we add it to the hot water, the gas is going to become a darker brown. So why is that? So if we cool the mixture, what the equilibrium wants to do is it wants to warm it back up again. So in order to do that, it shifts to the products, it shifts to the right so that it can heat the mixture up, because that reaction naturally heats the mixture up. So if we put it into ice, what happens is the equilibrium shifts to the right, which makes it a lighter coloured brown because it's producing more of the colourless N2O4, and it does that to heat the mixture back up because we've cooled it down. If you heat the mixture up, then the equilibrium is going to shift to cool it down. So the equilibrium shifts to the endothermic reaction, which cools it down naturally. Okay, so when we heat up the mixture, it turns a darker brown because it's making more NO2, sorry. So I've put a wee link there at the bottom to the Scholar. Now you can see this exact experiment in Scholar here. You can log into Scholar through your Glow. If you're unsure how to do that, please let me know. The way that I kind of think about temperature is with us ourselves. If we are cold, like if you just come out the swimming pool on holiday and you're cold, your body naturally shivers to warm you up and to get you back to your normal body temperature. And it's the exact same thing with equilibrium. The system is moving to heat itself up. If you cool it down, it's moving to cool itself down if you heat it up. So I hope you have paused the video and you've gone to look at that on Scholar now. The next one we're going to look at is the effect of concentration. And same again, we want to be able to describe how concentration affects the position of equilibrium. Same idea here. If we increase the concentration, the system's going to move to decrease the concentration. If we decrease the concentration, the system's going to move to increase that concentration. So the same process for each of these. So here we have a concentration of iron thiocyanate in equilibrium with separate iron and thiocyanate ions. Now, the iron thiocyanate ion solution has a red colour. The iron and thiocyanate solution has a yellow colour. And at equilibrium, the solution appears somewhere in the middle, a kind of orange colour. So here we have it. At equilibrium, it's an orangey colour. If we add iron ions, now the iron ions are yellow, so the solution is going to move to get rid of those yellow iron ions, and it's going to turn red. And if we add the thiocyanate ions, the solution is going to turn more red again, same reason, it's going to move to get rid of those thiocyanate ions, so it's going to make more of the iron thiocyanate. And if we add chloride ions in the form of sodium chloride, the solution turns more yellow, so we'll explain that on the next slide. So as I said, iron ion is yellow and the iron thiocyanate is red. If we add more iron ions, the equilibrium shifts right because it wants to decrease the number of iron ions, and it does this by producing more of the iron thiocyanate. If we add more thiocyanate ions, the equilibrium shifts to the right, again to decrease the number of thiocyanate ions, which is why, again, if we add more thiocyanate, it's going to produce more iron thiocyanate and it's going to turn red. And if we add chlorine, this removes iron. Now, the reason this removes iron is because iron chloride is insoluble, so that's going to precipitate out of the solution. And you're going to be left with less iron ions, so the equilibrium is going to shift to make more iron ions, and in the process it's going to turn yellow. So again, log into Scholar, try the interactive version of the concentration experiment on there, and then come back to this video. Next, we're going to look at the effect of pressure on the position of equilibrium. Now, when we're looking at pressure, we need to be thinking about molar volume. 1 mole of any gas takes up the same volume at constant temperature and pressure. That's what we need to be remembering. So, if we go back to our NO2 to N2O4 equilibria. So again, the mixture appears brown at equilibrium. Pressures only affect substances in the gas state. Pressure only affects gases, so we're only looking at gases. If it's not a gas, it's not affected by pressure. So in this case, we've got 2 moles of gas in the reactants and 1 mole of gas in the products. So if we imagine we've got the same volume, and on the NO2 side, that means we've got 48 litres of gas, and that makes it a high pressure situation. And in the same volume, because it's a closed system, it's going to be the same volume. It's going to just be a syringe or a bunged conical flask. There is the same volume, but there's half the number of moles of gas. So there is only 24 litres of gas this time, which makes it a much lower pressure system. So 1 mole of any gas takes up about 24 litres, we know that. So here they are, our 2 gases in this experiment. If we increase the pressure of the gas becomes a lighter brown. And if we decrease the pressure of the gas becomes a darker brown. So why is this happening? What is happening to the equilibrium position in this case? So if we increase the pressure, the equilibrium is going to shift to the right to lower the pressure, since there's less moles of gas on the right. So that means that when we increase the pressure, it goes to the lower pressure side of the reaction, the one with the less moles of gas. And in this particular case, that means it's moving to the colourless, which is why if we increase the pressure, it gets lighter. If we then decrease the pressure, the equilibrium shifts to increase the pressure again. So it moves to the higher pressure side, the side with more moles of gas. So in this case, it moves to the left because that's going to give us more, that's going to increase the pressure again and give us more moles of gas. Again, please pause this video here, go on to Scholar and try the pressure experiment on Scholar. What about adding a catalyst? So adding a catalyst changes the activation energy of a reaction. It does not change the equilibrium. So catalysts speed up how quickly equilibrium is established, but it does not change the position of equilibrium. Okay. So in order to do a wee recap of this, can you please go and watch this video. It is a crash course chemistry video. It's very detailed and it shows the experiments on the next few slides. I'm not going to talk you over the experiments on the next few slides because this is done in the YouTube video, but the next few slides will give you a bit more information about this. So please pause this, watch the YouTube video, and then come back and watch, look through these slides yourself on Teams.